A big part of science is finding patterns. Sometimes you'll see the same phenomenon occurring periodically, and it's useful to show these patterns visually. Perhaps on a table that shows the periodic pattern. Perhaps a periodic table, if you will. Like this one. Or this one. If you're feeling really fancy, maybe like this one. The periodic table is a chemist's best friend. It helps us find out all kinds of information about any given element at a glance. Yes, I see. So, one atom of calcium will bond with 2 atoms of bromine. Yes, I can see that. What's even crazier is that the periodic table was invented before we even knew about protons and neutrons or any other subatomic particle. Now, if you look at a periodic table, you'll notice the atomic numbers increase as you go across in rows. How in the world was a periodic table organized in order of atomic number if we didn't even know about protons and protons are the atomic number? Well, it started with observations. There are many elements we have known about for a long time, and scientists have made careful observations about them and learned things like their density, their reactivity, their atomic mass, some of the things they'll bond with, and even in what ratios. As a side note, we now know that atomic mass is the combination of protons and neutrons, but at the time they didn't know that. They didn't even know what protons and neutrons were. They didn't even know they existed. When the periodic table was created, we didn't know about protons or neutrons. We didn't know they were even parts of the atom. They were using relative weights of elements at an equal volume. It wasn't as precise as it is now, but they did the best with what they had. For a long time, chemists tried to find patterns in the properties of elements, but it was inconsistent and very frustrating. Then along came a super smart dude named Dmitri Mendeleev. He looked at patterns in the elements and found a pattern that nobody else had. He realized something was missing. There were holes. They didn't know all of the elements yet. Crazy. No one had thought of that before, because we're so smart, we know everything. One thing Mendeleev did is write down properties of all the elements he knew about at the time on individual cards, and he could sort them and organize them in a bunch of different ways to look for patterns and make sense. To demonstrate how Mendeleev did this, I'm going to take some paint cards and cut them up into little pieces. So here I have a bunch of little pieces of paint cards that I've cut up. I took 8 different colors and 5 shades of each color. I'm going to flip them back over and organize them. Now I'm going to organize these by color, with the darker shades on the top, well, farther away from me, and going down towards lighter shades. Okay, so I made my grid. Now I'm noticing that I started with 5 of each color, but I only have 4 of some of the colors now, so apparently I'm missing some. So I know I'm missing an orange, a yellow, and a gray. Is this gray? I don't know what color this is. And all of these started with deep shades and some mid shades. So it looks like I'm probably missing a middle range, right here or here. Yellow, a darker orange, and a mid to dark gray. But you may have noticed, I dropped some on the floor. Look at that. Yellow. Oh look, gray. So let's see, this one goes about here, the yellow probably goes about here, and the orange goes here. I was missing pieces. This is very similar to what Mendeleev did. You can think of the colors as the reactivity, what elements do, what they interact with, that kind of thing. Just like I could figure out some things about the color I was missing, Mendeleev figured out that there are elements missing from the periodic table. There were elements that we hadn't discovered yet. A good example of this is something called eka-aluminum. It was one step away from aluminum, so we called it eka-aluminum on the periodic table, and he was able to figure out a lot of things about it. Aluminum, and then your mystery substance. Based on where it is and the properties of the elements around it, he predicted it would have an atomic weight of around 68, density of 5.9, very low melting point. With oxygen, it would combine with 2 of the eka-aluminum, EL is eka-aluminum, and 3 oxygens. So that would look kind of like this. If the blue was eka-aluminum and red was oxygen, they'd kind of hang out near each other because it would ionically bond. And probably be discovered by spectrum analysis. That means that you need light waves to discover that it was actually a new element. And what was the reality of that element? Well, let's see. The element, eka-aluminum, is gallium. So he predicted atomic weight around 68. Atomic weight is 69.732. Density is 5.9. Its density is about 5.94. See, EL stood for eka-aluminum, so the real abbreviation is Ga. So 2 atoms of gallium bond with 3 oxygens ionically. It was discovered spectroscopically. Now, spectrum analysis means that when you light an element and put it and look at it through a spectrometer, you get different patterns. For example, helium will only give you a few little lines, but neon will do most of the colors on a spectrum. You can see gallium. Gallium has a very specific pattern. It's not exactly like germanium or zinc. It's a little bit different. They all have a slightly different pattern. That's how they were able to prove that it was a new element. Just like we can find patterns with the different shades of paint cards, we can see that on the real periodic table. For example, on the far left we have the alkali metals. They react violently with water, and they also react with halogens. Halogens are right here on the periodic table. Second column from the right. They really like to bond with the alkali metals. The alkaline earth metals, as the name implies, turn water into an alkaline state, or a base, the opposite of an acid. Over here we have the noble gases. They don't react with anything. It took a while for them to be discovered because they don't bond with things. They're in their own little world. They don't like to associate with anyone else. They're the snobs of the chemical world. Next we have the transition metals. All the metals in this lower middle section, right here, those are called transition metals. There are your stereotypical metals. You've got your iron, your cobalt, your tungsten, your gold. A lot of the metals you traditionally think of when you think of metals. Those are transition metals. So there are a couple ways you might see it on the periodic table. Sometimes you'll see little stars, sometimes you'll see an element or two here. But these are called the lanthanides and the actinides. And they actually fit in right here on the periodic table. The periodic table really should go whoop and have this extra row that just kind of sticks way out. But most periodic tables are two-dimensional, so we just kind of show they're down here. Once you get to the heavier elements on the periodic table, that's when you start getting into the radioactive stuff. Like all of your actinides, just all kinds of instability making them radioactive. Can you believe it? So far, 118 elements have been either discovered or created by humans. There could be more, but we run into the problems with nuclear stability at that point, because at the heavier end of the periodic table, you have elements that are so unstable that their half-life is fractions of a second, which means that they decay into something else pretty much instantly. It takes very, very sensitive instruments to even measure that they were there in the first place. There's a lot more information we can get from the periodic table. It's a very useful tool. Like with all resources, it's important to understand how the periodic table works. You don't have to have it memorized, you just have to know how to use it. It's useful to show that I'm going through puberty as a chemist's best friend. People are screaming outside the window. In the properties, elements, important, it's important. And it was discovered by spectroscopy. Useful tool. Oh, I know why I'm zoomed in. Ooh, scary. Into the radioactive table. The radioactive table. Okay.